Hello and welcome back, everybody. So really moving on to the second subsection of our overall section of matrix multiplications, matrix vector multiplications. And now we're here on vector multiplications. So rather than motivating directly the definition of the vector product, we're going to define it, but then we're going to talk about the geometric intuitions behind the vector product. So it's not something that you can really motivate directly, but once you have it defined, you can kind of describe what it's attempting to do, geometrically at least, since we'll talk about how to interpret it geometrically. So we're going to start with this product. Turns out there's multiple vector products. Not really a surprise from the fact that, if I have something like 3, -1, 0, and 2, 2, 1, what would make the most sense to multiply these two vectors? You can multiply it straight across, the 3 and the 2, the 1 and the 2, the 0 and the 1. That's called an element-wise product, but turns out there are lots of other products that make a lot of sense, and we're going to discuss a few of those today. So the first one actually we're discussing is the dot product, notated because it's got the dot in the middle, just like any other multiplications do. But we also give these the name inner product or scalar product. You'll see all three of them used interchangeably to refer to kind of the same operation on vectors. You'll see different notations for the scalar, inner, or dot product. The most common that we'll use in this book as well is truly the dot, as it's called. We also see these brackets. These are called angled brackets. Angled brackets. Or you'll see the notation where you take one vector and you put a t. It's called the transpose. You'll put the t next to the vector on the left. It always has to go on the vector on the left. You put the t next to that vector, and then you just write it adjacent to the second vector y. So any of those are equivalent notations. And the way this is defined is, it's going to make more sense if I draw these vectors. It's going to make more sense if I draw these vectors out, x1, x2, all the way down, xn minus 1, xn. If we say dot, y1, y2, yn minus 1, yn. What does it mean to take the dot product of these? Well, here I've written x1 times y1. That means I'm looking straight across x1 times y1, and then I add x2 times y2 straight across. I add eventually a bunch of dots, and then I add the second to last terms, and I add the last terms multiplied together. So I'm just taking multiplications straight across of the two vectors, and then I'm adding everything together. This should feel fairly similar to what we were doing with matrix products and matrix vector products, right? We were taking, in that case, the rows and the columns, and we were taking entries, multiplying them together, and then adding everything together. And if you're the sort of person who likes summation notation, I've got it there in summation notation as well. Now, this specific notation, x transpose y, reflects that the dot product is equivalent to the matrix product in the sense that, what does transpose mean? Transpose means exchange rows for columns, and vice versa. In the sense that if I have my x1, let's say x2 and x3, and if I write this as transpose y1, y2, y3, that transpose is telling me to exchange every row for a column and every column for a row. So it just rotates that matrix to become horizontal as x1, x2, x3, and now this looks exactly like a matrix product, because I can select the row here and the column there and perform the multiplication on the row and the column, and you still end up with this exact same sum. So that's where this dot product is arising out of. Let's go ahead and compute an example of it. These are pretty easy to compute. So here we've got 1, -1, 2, -2, dot product against 0, 3, -2, -2. What I'm going to do is go straight across, straight across, straight across, and straight across. I'm looking at 1 times 0, which is 0. I'm looking at -1 times 3, which is -3. Looking at 2 times -2, which is -4, and -2 times -2, which is +4. I'm adding all those together. We end up with -3. It's really not too complicated there. Now we're going to talk about the geometric properties of the dot product here. And to get into geometry, we're going to have to actually visualize one way of thinking about vectors. Now, a lot of students, especially if you were introduced to vectors in a physics course, believe that this is the only way to geometrically think about vectors, and it's not. There are many, many ways of geometrically thinking about vectors. This is the most natural, however. With finite dimensional vectors, the way I'm about to propose is the most natural way of visualizing them, geometrically at least. So these are called Euclidean vectors, named after Euclid. He's the father of Western geometry, so all of the geometry you learned probably in 9th grade, maybe 10th grade. So that's Euclid, who's the father, and so anytime you hear things as Euclidean, they're talking about flat geometries. So any sort of 2 or 3 dimensional space where parallel lines never intersect with each other. That's what Euclidean geometry is. And so to interpret a vector as Euclidean, we're just going to think about these vectors 1, 2, negative 3, 1, or 0, negative 2 as arrows in the two-dimensional plane, right? So the three vectors we were curious about was the vector 1, comma 2. And of course, this is equivalent to the point 1, comma 2. And if we plot the point 1, comma 2 in the xy plane, we end up with the point right there. But interpreted as a vector, this vector just emanates from the origin, and we give it a little arrowhead saying that it ends up at the point 1, comma 2. Our second vector was negative 3, 1, which we can think about as the point negative 3, 1. And the point negative 3, 1, of course, being plotted left 3 and up 1 is right here. But if we think about it as a Euclidean vector, this is the arrow starting at the origin and ending at this point. Finally, the last vector that we were shown was 0, negative 2, which we can think about as the point 0, comma negative 2. So if I plot the point 0, negative 2, I move to the right 0 units and then down 2 units to this point here. And as a vector, we think about it as an arrow emanating from the origin. And so these are going to be considered Euclidean two-dimensional vectors. And once we think about them as these arrows which exist in two-dimensional space, we can start to ask geometric questions about the vectors. Most notably, the first one we're going to encounter, like the angle between any two of them, right? Each of these vectors are going to have angles between them. And we'll be able to compute those angles using some of these vector products. If we want to think about vectors in 3 dimensions, we do it basically in the same manner. So this vector 1, 1, 1, think about as the point 1, 1, 1, which we've learned how to compute in 3 dimensions, or plot in 3 dimensions. At least you move to the right 1 unit, forward 1 unit, and up 1 unit. So you end up at this point 1, 1, 1. And then we think about the Euclidean vector as the vector emanating from the origin and ending at that point 1, 1, 1. Similarly, this point 0, negative 2, 1, or the vector 0, negative 2, 1, we think about as the point 0, comma negative 2, 1, and we learned how to plot those. We go to the right 0 units and then backwards by 2 units because that's the negative y direction. And then we go up 1 unit and we end up at our point 0, negative 2, 1. I don't know why I have a 1 here. It should be a 0. 0, negative 2, 1. And then we think about the Euclidean vector as the vector which starts at the origin and ends at this point 0, negative 2, 1. And then finally, our last vector here, we have negative 1, negative 2, negative 3. We think about that as the point negative 1, negative 2, negative 3. And if we plot that point, we go left 1 unit, back 2 units, and then down 3 units to the point down here. But of course, the vector is the vector which starts at the origin and ends at that point, negative 1, negative 2, and negative 3. And even in 3 dimensions, right, these Euclidean 3-dimensional vectors can be thought of geometrically. We can even ask about the angles between these vectors, and we can ask some other important ideas like the total length of the vector, for example. Now, the length of a vector should probably correspond, since it starts at the origin and ends at the point, to the distance formula between the origin and that point. But we'll see we give the name of the length of a vector a different name than just the distance to the origin, because we're not referring to points anymore. We are referring to the entire object, which is this arrow. So we will start with that and talk about the length of a vector. And the new name we give the length of the vector is the magnitude, or sometimes we give it the name norm as well. Okay, so magnitude, length, or norm are all the same when it comes to vectors. You'll hear people refer to those interchangeably. And the way we actually compute it is you take here's the dot product showing up. That's why we started with the dot product. You take the dot product of a vector with itself. And that's actually going to give you the length squared. So if I just naturally did x dot x, this is going to be the length of x squared. If I want to compute the square root to get the regular length, I just add the square root on the left side. So you see that the square root of the vector with itself gives the length. And if you think about it, this x1 squared really is, x1 minus 0. It's the distance between that part and the origin, the 0. We are using the distance formula here, but now that we have the dot product at our disposal, we have a nicer way of representing anything. So the square root of the dot product with itself gives the magnitude or length of a Euclidean vector. Let's actually compute some of these. So if I want to compute the length of the vector 3, negative 4, how do I do that? Well, we recall the way to compute the magnitude is by taking the square root of the vector dot itself. So I'm going to do the square root of the vector dot itself. And how do I take a dot product? I just work horizontally across and add all the terms together. So we end up with 3 times 3, or 3 squared, plus 4 times 4, 4 squared. We get 9 plus 16, we get 25. The square root of 25 is 5. Similarly, if I want to compute the norm of the vector 1, negative 1, root 2, I can do that. As before, it's just the norm is the square root of the dot product of the vector with itself. I'm going to work horizontally across for the dot product. I have 1 times 1, 1 squared. I have negative 1 times negative 1, negative 1 squared. I have root 2 times root 2, root 2 squared. I add all those together. I have 1 plus 1 plus 2, or I have root 4. I happen to have 2. Now, if I go ahead and plot these vectors, maybe you'll actually believe me a little better about the vector 3, negative 4. I'm going to go out 3 units in the x direction, 4 units in the y direction. That length ideally is 5. I'll draw it in purple here. So we expect this length to be 5. Well, yeah, it should be 5 because this is a 3, 4, 5 right triangle. Same idea with that if you decided to plot it in 3 dimensions. So we have something called a normalized vector as well. And this is where you take any vector and you divide that vector by its norm. And I'll put dividing in quotes here, a vector by its norm. Why do I put dividing in quotes? Really, this is a scalar multiplication by a reciprocal. So, if I divide by 2, it's the same as multiplying by 1/2. So that's how we think about dividing here when we have the norm. We call a vector normalized if it has already been divided by its norm, okay? And normalized means, since it's already been divided by its norm, the new norm, if I were to take a norm of this vector, the new norm would have to be equal to 1. There's no way to escape that the new norm is going to be 1 once it's been normalized. So let's look at a normalized vector here. We have the vector 1 over root 2, negative 1 over root 2. And we can tell it's normalized since, let's compute its norm. We compute the norm by taking the square root of the first entry squared plus the second entry squared, right? Square root, if I did the dot product with itself, that's just going to square the first entry and then add squaring the second entry. So if I go through that work, 1 over root 2 squared is 1/2. Negative 1 over root 2 squared is also 1/2. I get the square root of 1. This is normalized, as long as the norm is equal to 1. The second vector we have here is not normalized. Negative 3, 0, negative 4. We can tell it's not normalized by computing its norm. How do you compute the norm? As always, we're taking the square root of each entry squared. Negative 3 squared, 0 squared, negative 4 squared. You get square root 9 plus 0 plus 16, root 25. But since 5 is not equal to 1, when the norm is not equal to 1, we say it's not normalized. Now we can also go through the process of normalization, which means we divide by the norm, as discussed previously. So here we've got the vector negative 12, 5, and this may or may not already be normalized, but we can certainly find out by computing its norm. We're going to square 12. We're going to square 5. We get 144 plus 25, which happens to be 169. Take the square root of that, and we get 13. So the norm is equal to 13. To normalize, right, if I scroll back up here, to normalize a vector, we're going to take it, we're going to divide it by its norm. And to divide by something means to multiply by its reciprocal. So we are going to take this 13. The reciprocal of 13 is 1/13. We're going to go ahead and multiply the vector by 1/13, and we end up with negative 12/13, 5/13. Turns out if you would compute the norm on this vector, you would have to get 1. That's what the process of normalizing does. Maybe I should discuss why normalizing is important here before we do too much of it. This is important because normalized vectors are a unique way to discuss directions. Okay, you can think about a normalized vector as a representation of a direction in space. Vectors themselves, as plotted up here, represent both magnitudes and directions. They have a length, they also have a direction, but there are certainly worlds in which we only care about directions and not about lengths. And this is what the act of normalization gives us, is an ability to discuss directions alone and not lengths. If we say, okay, that length of, we're going to send the length of every vector to be equal to 1, then the only questions we're asking about are directional questions, not length questions. And that can definitely be a useful thing to discuss. Think about an airline pilot who needs to center the plane in a specific direction. They would ask about the vector, but they really care about a unit vector or a normalized vector in that specific direction. We can normalize this other vector 1, negative 1, root 2 as well by first computing its norm, we're going to square 1, square -1, and square 2 to get 1, 1, 2. Add them together, we get a 4. The square root of 4 is 2. So if we're going to normalize this, we take the reciprocal of 2, which is 1/2, and we're going to take that 1/2 and multiply it against every term in the vector. So we get 1/2, -1/2. And actually, root 2 divided by 2 is root 2 divided by root 2 times root 2. One of those can cancel, and you get 1 over root 2. So that's why I've written it as 1 over root 2 there. Another example of normalization. And so this is actually maybe our first example of why we would care maybe about normalized vectors instead of just vectors as a whole. If we're asking about angles, or if we're just asking about how I've written it here, parallelness, like how parallel are two vectors to one another. This is a question uniquely about direction and not magnitude, right? We don't care about magnitude at all. We only care about direction when it comes to parallelness of vectors. And so the process of computing parallelness inherently incorporates a normalization procedure, which you can see here. We've divided x by its magnitude and we've divided y by its magnitude. So it turns out if you take any two vectors, interpreted as Euclidean vectors, and you divide them by the product of their magnitudes, in other words, you normalize them, that dot product will always be equal to cosine of the angle between the two vectors. Or in other words, if you're looking specifically for that angle between the two vectors, you can just go ahead and compute the inverse cosine of x dot product y divided by the magnitude of x times the magnitude of y. And then this will give you the angle. So that's kind of nice. The dot product can give us the angle between Euclidean vectors as long as we normalize the dot product. Now this is the minor angle, right? Because if I take that arrow and this arrow, there are actually two angles between them. There's the inside angle and the outside angle. We call the smaller one the minor angle, so this will always give us the inside angle between the two vectors. Okay, there are some specific cases of this. The specific case occurs when the angle between the vectors is 0, at which point they are completely parallel. And so you end up that the dot product is actually equal to the multiplication of the magnitudes, because if I evaluate cosine at 0, I just get 1 here. There's the specific case where the angle between them is pi over 2, also known as perpendicular vectors, or we use the word orthogonal vectors. And this is going to occur specifically when the dot product between two vectors is equal to 0. And finally, if the angle between the two vectors is pi, right, that's a 180-degree rotation, then the vectors are still parallel, but they're pointed in opposite directions, right? You can think about one vector pointing here and its friend pointing here. That's going to be an angle of 180 degrees between the two of them. You're going to find out that the dot product is the negative of the two norms multiplied together. I think I should emphasize this middle one a little bit more because it gets used all the time. It turns out that orthogonal vectors are well behaved. And so a lot of scientists, a lot of mathematicians like to find these. We like to find these out in nature, or even when we're developing mathematical models. I mean, all of quantum mechanics is kind of based around orthogonal vectors, so abstractly, of course. But there's this notion of orthogonal vectors. They happen to be very well-behaved vectors, and so we care a lot about dot products of vectors being equal to 0. So this is something that we're going to be searching for quite often, whether or not in this class. You might see it in physics classes as well. I should say that one of the natural reasons why orthogonal vectors are well-behaved is if we just think about any number of dimensional space, but I'll just put the three-dimensional space on the board here with the x, y, and z axes on the board. Let's think about the vectors which exist in their respective x, y, and z directions. So I could call this the x vector if I want to. I could call this the y vector if I want to. And I could call this the z vector if I want to. Those three vectors, of course, do happen to all be orthogonal to one another, right? So that's just like kind of a classic case of orthogonal vectors being very well behaved. They describe our natural three-dimensional space quite cleanly. Okay, so let's go ahead and find the angle between the two vectors shown here. I want to find the angle between 1, -1 and -1, 0. How am I going to do that? Well, let's just recall the formula really quick. It's x dot y divided by magnitude x dot magnitude y equals cosine of theta. We're going to go ahead and compute the dot product in the numerator. We're going to compute a couple norms in the denominator. And what happens when we do the dot product here? We have 1 times -1. We have -1 times 0. So the numerator is going to become -1 plus 0. Numerator becomes -1. The denominator is going to be the magnitude of 1, -1. So I'm going to square both entries. 1 squared, -1 squared. I'm going to get a square root of 2 on that magnitude. My second magnitude, I'm going to square -1, and I'm going to square 0. I'm going to get a square root of 1, also known as 1, as the other term of the denominator. So it turns out here that this quantity that we're going to use to calculate the angle is equal to -1/√2. Well, because this quantity has to be equal to the cosine of the angle between the two vectors, we're just going to go ahead and compute cosine inverse on both sides, recovering theta. Cosine inverse of -1/√2 happens to be 3 pi over 4. Right? We might want to send ourselves back to the unit circle here, specifically in this direction, which is 3 pi over 4. On the unit circle, we get an x value, -1/√2. Okay, so the angle between these vectors ends up being 3 pi over 4. If I plot the two vectors, what do you know? The angle between them is precisely 3 pi over 4, exactly like we would expect. We can do the same thing with some three-dimensional vectors, so let's do that here. We've got 2, 5, 6, -2, -4, 4. And remember, my formula for the angle x dot y divided by magnitude x dot magnitude y equals cosine of theta. So I'm going to compute the dot product of the two vectors in the numerator, meaning 2 times -2, 5 times -4, 6 times 4. Add those all together. It turns out we get 0 in the numerator. In this sense, it doesn't really matter that we calculate the denominator as long as it's non-zero, which it does turn out to be non-zero, because the numerator gave us a 0. This is that nice situation I was talking about where we find that the dot product of two vectors is 0. This tells us they are orthogonal, which is our fancy word for perpendicular, which also means the angle is pi over 2, angle is 90 degrees, whatever you want to think. If we go ahead and plot these two vectors in 3 dimensions, it looks like the following. Of course, as always, this is projected onto a 2-dimensional screen, so it might be a little hard for you to tell that indeed these two vectors are orthogonal to one another. There's the right angle I've thrown in there. So one of them's pointing out of the screen, the other one's pointing back into the screen. So they are definitely orthogonal to each other. It's just hard to see. We can even find the angle between some 4-dimensional vectors here. I mean, we start to lose our intuition as to what it means, because we can't visualize geometrically 4-dimensional vectors, but there's nothing preventing us from going through the motion and calculating a theta that somewhat represents what's going on. So moving onwards, we've got something called the cross product. So this is a new product that differs from the dot product and is special, I'll say, and only exists. So it's special because it only exists in 3 dimensions. It's kind of a really cool fact that's going to take us maybe another month to encounter why it's a cool fact. And even the reason why it's a cool fact is a bit of an anecdote in this course. You really need a course in differential geometry to fully appreciate what's going on with the cross product. But it's something special that happens in 3 dimensions. So we have 2 3-dimensional vectors here, and I've kind of changed up the way I notate my vectors. In the past, I would have x1, x2, x3, and y1, y2, and y3. Kind of change these up to say x, y, and z in both of them because they refer to their respective directions in 3 dimensions. But if I have 2 3-dimensional vectors, x1, y1, z1, and x2, y2, z2, I can define this object called the cross product between the two of them. We're going to notate it with the times symbol, the x times symbol, or a cross, right? That's what's called the cross product. And for now, we're just going to memorize it as the following identity. So the way we compute this is if I'm looking for the x output, how am I going to find the x output? I'm going to remove the x from the input, and I'm going to start to draw some crossing lines. So this is why we call it the cross product. So I'm going to draw a crossing line here and a crossing line here. And that first crossing line of y1 on z2 is going to be my first product. And then the second crossing line, z1 on y2, will be my second product. And then those 2 lines get a minus sign between them. If I want to find the y output, then I'm going to cross out the y terms, and I'm going to start to include my crossing lines. I've got an x1 and a z2. I've got a z1 and an x2. But there's a little downside here, and that's that I don't work top left to bottom right. I work bottom left to top right, specifically in the y output. This is flipped compared to the other 2 outputs, okay? So I'm going to work bottom left to top right. I'm going to get z1, x2 as my first product, still the minus sign. Then I'm going to work top left to bottom right. I get x1, z2 as my second term in the y output. If I want to do the z output, I'm going to cross out the z lines, and then I'm going to include my cross terms here, x1 on y2, y1 on x2, and I start on the top left, move to the bottom right. I get x1, y2, and then a minus sign, bottom left, top right, y1, x2. So that's how I think about it. That's how I actually memorize it in my head. I always have to remember that the y direction is flipped. But you could just memorize the formula directly, right? It's not going to take you too long to actually memorize the formula right here. So totally up to you how you want to remember the cross product, whether or not you want to memorize it. We'll talk about what this means geometrically in a bit, but we're just going to go ahead and compute the cross product for now. So here I've got two vectors, 1, -1, 2, and -2, 0, 3, for which I'm going to compute a cross product. Now let's remember how at least I remember this. In the x direction, I'm going to cross the x direction out. I'm going to draw my cross lines here, and I'm going to multiply -1 on 3. There it is. I'm going to multiply 2 on 0. There it is, and I've got a minus sign between them. So -1 times 3 minus 0 times 2 gives me -3 in my first output. If I want to find the y directional output, I'm going to cross out y here. I'm going to include the cross lines. And then in the y direction, things get flipped. So rather than starting on the top left, I'm starting on the bottom left. So I get a 2 times a -2. There's my 2 times -2. Then I subtract a 1 times a 3. There's a 1 times a 3. So that ends up being what? -4 minus 3 gives me -7 as the y output. And then finally in the z output, I'm going to cross out the z direction. I'm going to include the cross lines. And then I work on the top left to the bottom right, 1 times 0, minus the bottom left times the top right, -1 times -2. If I add all those terms together, 0 plus minus, so 0 minus negative, so an overall minus 2 is going to be -2. And so the cross product between these two vectors is the third vector here. You might wonder why we've even introduced something like the cross product. Well, that's what this next proposition includes, is the geometric properties of the cross product. If I compute the cross product of two vectors, it just so turns out that this cross product will necessarily be orthogonal to both of the earlier vectors. Remember, orthogonal is our fancy word for perpendicular. It's our fancy word for 90 degrees to each, right? Each x and y. Now, this is very special because in 3 dimensions, there's really a unique direction that's going to be perpendicular to any two other directions, right? You're looking at your computer screen right now. If I put this vector on your computer screen, and think about it like inside the computer screen itself, and I also put this vector inside the computer screen, there's only one 3-dimensional direction remaining. It's the one that's pointing straight out at you, or, it's negative, which is the one that's pointing straight into the computer screen. But those are the only two other directions that's perpendicular to both of those first two vectors. And so it's quite special to find that third direction when you're working in 3 dimensions, and that's kind of cool that we have a very efficient way of finding it. But that's actually not all. The cross product does one extra thing for us, and the extra thing that it does for us is the norm. If I take the norm of that cross product, that norm is going to compute the area of the parallelogram with two sides corresponding to the vectors x and y. Okay, so going back to me drawing some stuff into the computer screen, maybe I put one vector here, and I put another vector here. Those two vectors form the sides of a parallelogram in the sense that I can translate the bottom one upwards, and I can translate the left one to the right and get this parallelogram here. If I decide to compute the area of this parallelogram, this area right here, it turns out all I have to do is find the cross product of these two vectors. So I'm going to take the cross product of those two vectors, then a magnitude. If I take the cross product and the magnitude, I'll find the area of that parallelogram. So it's kind of fascinating thing that we get out of this slightly strange definition of a cross product. So now I'm going to provide examples of the geometric properties of a cross product. Let's go ahead and compute the cross product of 1, 1, -1 with -1, 2, 2. If I do that, remember how I get the x component, I'm going to cross it out, and I'm going to add my crosses in here. I'm going to take 1 times 2 minus -1 times 2. I'm going to get a 4 for my x output. If I want the y output, I'm going to cross out y here. I'm going to take -1 times -1, and then a 1 times a 2, and I'll get really a 1 minus 2, so I'll get -1 as the y output. And then finally, if I want my z output, I'm going to cross out the z direction. I'm going to say 1 times 2 minus 1 times -1. That's going to give me a 3 in the z direction. So this vector for -1, 3 will be the cross product of the other two. And, if I want to verify that this is orthogonal to each of the first two, so if I want to say that that's orthogonal to that, all I have to do, recall orthogonality, says x dot y is equal to 0. It's that very special case of finding the angle between vectors. Let's go ahead and compute the dot product here and verify that it's equal to 0. So the dot product is just going to be the first entry times the first entry plus the second entry times the second entry, third entry times the third entry. We do indeed get 0 out of that dot product. I can do the same with the second vector here. and say maybe I want to verify that I'm orthogonal to the second vector, all I have to do is take the dot product of those two. When I take the dot product of those two, I'm going to have a 1 times 4, a 2 times -1, and a 2 times 3. And we do indeed recover 0 there as well. If I decide to plot these, you can also verify that the third vector over here is orthogonal to the other two. I mean, it's a three-dimensional vector, so it's a little hard to see in the screen, but we do have a right angle there. We have a right angle here. And the first two vectors weren't necessarily orthogonal to each other. It's just that the green vector is definitely orthogonal to the other two. If I want to compute the area of the parallelogram between those two vectors, now that's a really kind of a funky thing. So here I've already plotted it. There's me embedding the parallelogram in 3 dimensions. If I want to calculate the area of that parallelogram, all I have to do is look at my answer here, right? So the answer of my cross product was 4, -1, 3, and I'm going to go ahead and compute the norm of 4, -1, 3. You'll recall the way we compute a norm is we square that entry, we square this entry, we square this entry, and then we take a square root of everything. And that's going to give us, in this case, root 26, approximately 5.1. It's a little hard to tell in the picture that it should be approximately 5.1 units, but this is actually a true fact. So it's something that's very interesting about the cross product. So that's all I've got for now. Next section, we're going to get excited thinking about matrix powers, inverses, and the identity matrix. I'll see you then. Bye.